And now we have a presentation by Dani. So I will stop sharing and turn it over to her.
All right, all right. Hello, everybody. I apologize if I start to get the crazy eyes with like looking around the screen and not looking into the camera, but thank you for inviting me for a second time to speak with you today. I had a lot of material that I could have prepared for today, but I figured try to keep it a little on the shorter side because, you know, the Zoom call maybe make good for some questions and discussions and things. And, you know, just if there's anything we didn't talk about that you want to bring up, you know, we'll be happy to go there. So, you know, let's go for it. So, you might be well aware that March 6, 2020, Pennsylvania reported its first detected case of COVID-19. And here we are a year later. And, you know, I'm sure this year you've learned more technical virology terminology than most of us thought we ever would. You know, the situation in the early days was very confusing, even to experts and medical professionals who just didn't have all the information they needed. And everything was just so new. But, you know, a tremendous amount of people have been working very hard and have uncovered a lot in a short amount of time. And it makes it easier for us to kind of think about what's going on. And, you know, we can really accomplish a lot by working together. So just, you know, before I really start getting into it, I always have like my disclaimers. So my disclaimer today is that that I'm going to talk a lot about vaccines today. And I'm not going to talk about any like specific company, but I do work for the pharmaceutical industry, but I don't work for any of the companies that I'm going to discuss today. So I don't have any kind of inside knowledge or anything like that. All of the information I'm going to present today is publicly available, and it's all publicly shared. So, you know, there's nothing proprietary or technical that I'm going to talk about today. But yeah, let's get into it then. So the big question that I sometimes ask myself is, why is COVID-19 so different than anything we've seen before? You probably remember this picture that I showed in my last talk, and we were talking about how the colds infect your upper respiratory system and flu infects the lower respiratory system. And the difference is what makes one basically harmless and the other not. So, well, surprise.
Excuse me, Dani. I don't see your PowerPoint progressing. Like I still see the cover page.
Oh, okay. Let's see what's going on here.
I don't know about anybody else, but
anybody else have that problem? Okay, yeah. Let's see what's happening here. Can you see the presentation now?
Yes, thank you.
All right, let's see. It's
but it's got scribbles on it and stuff.
Yeah, that's strange. All right, and
I think I did that.
I guess you can't see it now.
Sarah. I think Sarah is annotating. I will yell at her.
Oh, oh, let's see. Well, I mean,
nope, that looks good now. Yeah.
Okay, I'll just do it this way. Let me see if I can use my arrow keys. Before I would have the certain things come onto the screen at different times, just so you're not overwhelmed. But I'll do it this way because it seems to be working a little better. Let's see. Let me just see if I can. And I guess you can't see that. All right. Well, all right. Let's do this. All right. So can you see my mouse pointer? Okay, just making sure, because I'll just point to things just so we can direct our eyes so we're not overwhelmed by information here. So anyway, I was just referring to this little picture of the lungs and the mouth. We were talking about upper respiratory versus lower respiratory tract infections. And you know, the big surprise with COVID is that it infects both. So it's kind of contributing to this like really big range of where some people have, very minor or no symptoms at all, and other people are dying. And this idea that, you could be in this period where you're spreading virus before you're feeling very sick. And that has to do with, kind of having that upper respiratory infection, maybe before you get to the lower respiratory infection. And it's making things very different than we're used to. So I put a little chart here that compares flu and COVID-19, just because like when we talk about some of these numbers, you need some kind of basis for comparison. I know in the beginning, like the comparison to flu might have been counterintuitive because we're like, oh, it's kind of like flu, but we just need some numbers to compare to. So COVID is just so much more contagious than the flu is. We'll have like flu, one person might infect, the average is 1.3 others, but COVID, it's like 2 to 2.5. Another thing that complicates how contagious it is the number of days before you really start to see symptoms, where flu 1 to 4, COVID 2 to 14. So this could be anywhere from like 2 weeks later. If you're trying to find out like where it came from, possibly where someone got infected, like I sometimes have trouble what I exactly did 2 weeks ago. It's hard to remember, like, oh, who did I come in contact with? It just makes the contact tracing so much more difficult. So in terms of hospitalizations and deaths, like these numbers are just very large compared to flu. Whereas I know earlier on, it was kind of, we weren't really sure what these ranges were because it was still early on, but now it looks like, just the magnitude here is very serious. Ultimately, when we think about deaths here at the bottom of the chart, like these lower respiratory infections is what get really dangerous because of the way our immune systems try to fight the virus. So inflammation, like the virus in the lungs causes inflammation in the lungs. This can render lungs unable to clear debris and fluid and can even damage the lungs. And if the rest of the body isn't getting enough oxygen, it leads to organ failure. We're just beginning to understand the long-term effects of some of these reactions, but there's more and more evidence that this is also a disease of the circulatory system as well as the respiratory system. Evidence of certain individuals are more prone to getting blood clots, especially after the initial infection is cleared. So this extreme variation of symptoms is sometimes very difficult to react to. So you can have some people spreading the virus with no symptoms while other people are dying. And this odd in-between makes it difficult for someone to know how to react. So like on one end, panicking is not helpful, but doing nothing is also not helpful at all. So I can understand why some people are like in complete denial that there's a problem, but then there's other people that are so afraid of leaving their houses that they might be like dying of preventable illness if they won't go see a doctor. So finding an in-between is a challenge with this new situation. So any new virus with no existing drugs to fight directly, what's the best plan to protect ourselves? So the answer is to make a vaccine, but that's not going to happen overnight. So it was initially thought 12 to 18 months, before something could get approved. And then it's another story on like how long it takes to actually get people vaccinated. So in the meantime, people were getting sick way too fast. If you have everybody at the hospital at once, that's not good for anybody. So waiting for drug development, the idea is that, we're going to have to employ public health measures to kind of buy some time until we can actually like come up with, solutions for this problem in terms of vaccines. So where am I going here? Okay, hold on. So yes, public health measures are kind of where we're at in terms of trying to save ourselves some time before we can, roll out all these solutions, using the technology that's been in development for nearly 50 years to build some of these vaccines that have been approved at this point. So I feel like I'm always slightly behind on these presentations because, things are moving at a fast rate. And now the Johnson & Johnson vaccine is approved. We have the Pfizer and Moderna. So forgive me if I seem a little behind here, but I'm going to discuss a little bit about mRNA vaccines and the 50 years that kind of led to their development and the launch of these types of things. So here I'm showing a kind of summary of the vaccines that we had available until this point. So the earliest vaccines were live attenuated vaccines, which is live virus that's been weakened in some way. This was the first vaccine that was ever developed was for smallpox. And this was the way it went, rabies and some of the other earlier ones. Most of the modern ones that we still use, there's the MMR vaccine is live attenuated. The flu mist, oral polio vaccine is live attenuated. Then, like as time moved on, we moved on to these inactivated vaccine, which is basically dead virus. There's the injectable flu vaccine is this hepatitis A. The injectable polio vaccine, which came a little bit later, is inactivated. Later came the subunit vaccines, so you might recognize some of these as like fairly new within, or at least my lifetime, HPV, hepatitis B, Shingrix, which is for shingles. They work by just taking a protein, a single protein or a subunit of the virus, as opposed to the whole thing, and using various ways to make these. These tend to be not as strong as the previous ones. These ones typically involve boosters or some other kind of thing. But then the most recent ones before the ones I'm going to talk about are the viral vector vaccines, which is taking a different virus, putting the genetic material of the virus of interest in here, and then using that as the vaccine. So there's been several Ebola vaccines that are under clinical trials. The AstraZeneca COVID vaccine and the J&J are both this kind, but we're not going to talk too much about that because it's a technology that has been used for other things in the past. But all of these vaccines have this disadvantage in that they involve having to grow large amounts of live pathogens in a lab in order to make them, which can be very time consuming, could be dangerous, could be, a number of disadvantages in trying to get these things moving quickly. So they, where am I at here? So a lot of these too involve like thousands of animals to grow these up if we're not able to grow it in cell culture. I'll give you a specific example of the development of the first measles vaccine in the 1950s, or excuse me, the 1960s. And the measles vaccine that we use today is a little different, but this was the original measles vaccine. So it took 10 years to make this vaccine because in order to do so, the virus, the live virus, had to be weakened enough so that it wouldn't harm people, but it could still cause an immune response. And the way that was done was injecting rabbits, one after the other, taking the virus from one rabbit and passing it on to the next rabbit and passing it on to the next rabbit. And each time the scientists were selecting for a weaker virus every time. So this was not easy to do, and there actually wasn't a whole lot of support at the time to fund it because in the 1960s, in Western countries, measles was just accepted as an unpleasant part of childhood, even though it had a mortality rate of 5% in children. And that was higher than polio at the time. And in West Africa, for children under 5, the mortality rate was 50%. So this was something that, even if it was considered not a big deal in North America or Europe, was a major deal in West Africa. But let's see, it was, yeah, so I'm trying to like change my slide here. Oops. Sorry about this. Oh, there we go. Okay, so the 1970s is when the work first started that would become the RNA vaccines that have been approved just recently. It was 1971. It was first figured out that you can take a piece of RNA, which is the message that ends up making a protein. You could take a piece of RNA from a rabbit and you can inject it into a frog embryo to get the rabbit protein. And this had implications for a lot of different technologies at the time. And it's not like Jurassic Park, where you're taking the dinosaur DNA and putting it into the frog proteins. This is just the RNA to get a single protein. But the RNA, the message that the DNA makes, it's very fragile compared to DNA. It doesn't stick around very long. It's not meant to be permanent, and it breaks down in the body really easily. So it's not like we're doing the type of like genetic engineering that happened later in the 90s. This is just kind of trying to see if we can get one species to temporarily make proteins from another species. So down here, I kind of have the next step, where it was investigated to see if, excuse me here. So I'll explain how the old vaccines that we have kind of work by, you'd have these large whole viruses injected into someone's arm, and the immune system would recognize it, and you'd get an immune response. But then it was thought that, oh, maybe we can use this RNA technology to get the little piece of the RNA into the body, not the whole thing, and just make the protein that the immune system is going to recognize. And that way it could be a little easier without having to inject the whole thing. So there was a problem with this, though, in that injecting this little piece of naked RNA didn't really stick around long enough to make viral proteins to get an immune response, because this little piece of RNA on its own wasn't causing the immune response. It was the viral proteins that it was going to make. So their major roadblock was just how to fix this problem. We'll go on to the next slide. So let's see. So this was originally supposed to be an animation, so I apologize if it's like too much. But so the idea was that the RNAs are getting injected, but our bodies, they don't like to see these little bits of RNA just on the outside of the cell before they get inside the cell. The reason for this is that free-floating RNAs are seen by the body as a potential danger because they can be the remnants of cancer cells or cells that have already been infected by viruses. So we have these little things called RNases that come and like eat them up. I kind of represented them as little Pac-Mans here. They'll eat them up before they ever have a chance to get into the cell, make the protein, and have the immune system recognize it. So there had to be a solution to how do we get these things inside of the cell before the immune system comes and eats them up too soon. So enter, let's see, here we go. Enter the lipid nanoparticle. So lipid nanoparticles were first developed in 1978. They're little balls of, I call them little balls of fat. You can put a bunch of different things inside of them. It could be a drug, and in this case, the pieces of RNA that we're talking about. They're a way to deliver these little RNA pieces to the cells and protect them from getting chewed up by these RNases. So some of them can have other parts connected to it, like a targeting antibody or another kind of drug. They can get it to the area of the cell that it needs to be. I had the privilege in 2014 of helping to develop and test a drug made with this technology for a liver treatment, whereas a little piece of RNA was going to go to the liver to make a protein that was deficient in certain liver diseases. And we were trying to look for ways to get the little lipid nanoparticle to the liver and not other places. Like, we were looking at is it in the kidneys, which means it's just passing right on through. But in 2018, the first drugs using this lipid nanoparticle technology were approved by the FDA for commercial sale. And it was in 2018 that scientists realized, oh, wow, okay, so we already have, the kind of framework for the vaccines, and we can definitely launch them now. So there are several advantages to vaccines using this lipid nanoparticle technology. The most important is that they're very fast to make and modify. So once you have the basic pieces to make an RNA vaccine in place, you don't need an entirely new setup to make a new one every time. You might have heard the term plug and play with these. Once you have the device, you can just take whatever piece of RNA you need and swap it in and out. Almost like if you want to listen to a song, you don't have to build a new record player each time. If you just have a series of records, you can just put the new one on into the existing framework. So I don't know if anyone's heard the term adjuvant before, but lipid nanoparticle vaccines don't need adjuvants. And an adjuvant is it's an extra ingredient that goes in vaccines that enhances the immune system even more, because sometimes you don't get a very strong immune reaction with a more traditional vaccine. Adjuvants tend to be aluminum salts, but to know how much to add, the different formulations for each type of vaccine, that's usually what can take a long time to develop, because you don't want too much, you don't want too little, kind of modulating that immune response. But it seems like these lipid nanoparticles, they're really good at triggering immune response on their own. Once the drug, once the RNA gets into the cell and makes the viral proteins, a lot of your immune cells are coming to the area without any need for additional ingredients. So there's a current work that's being done to develop treatments for bacterial diseases and even some cancers using this technology now. So be on the lookout in the future, because it seems to be a really promising technology that you'll probably see more and more of as things start moving along. So let's see, we're going to kind of switch, because we're talking about vaccines now, and how do vaccines kind of relate to these COVID mutations that are happening. So like we talked about last year at the previous talk, when somebody gets infected with a virus, the virus replicates, and small mistakes can get made when the genetic material is copied. And this is especially true with RNA viruses that tend to make more copying errors relative to other types of viruses, such as DNA viruses. And the errors can be harmless in terms of they don't change the virus at all. We call these silent mutations. They could make the virus, let's say, less harmful to humans, which is kind of a good thing. But then we get the unlucky situations where a mutation in the viral genome makes the virus somehow better at infecting or better at killing, and that's not what we want to see. Let's see. Yeah, I like to kind of look at this quote here. Viruses are going to do this no matter what. It's just a matter of making sure it's not happening as fast. So I'm sure you've seen this picture a lot with the ball with the little red spikes coming out of it. I don't know why they make them red in all the pictures. It could be any color, but this is the spike protein of the virus. And most of the harmful mutations, these variants that have been being discovered, all involve this spike protein because it seems to be the most important protein on the virus in terms of infection. So let's take a closer look at this red thing. Look at these two pictures up here. Here's a close-up of the spike protein. It's made of 3 subunits, which is kind of hard to see here, but there's like 3 petals on this flower as we kind of talk about it. And it can be in 2 conformations. This is the closed conformation, and then there's also this open conformation. And the virus, the original virus from 2019 that came out of China, it tended to be in this closed conformation more often than the open conformation. And it was sometime in the winter of 2020 that there was a mutation the first mutation that happened in this protein that made it so that the open conformation was more common. It was just staying in that open conformation longer. And this picture down here is showing that when the virus binds to a human cell, it's in this open conformation that it really attaches strongly and can enter the cell more quickly. So let's see, this is the mutation. So this is another way of looking at the same protein. The mutation happened down here, and we call it D614G. We use these kind of alphanumeric notations to talk about these mutations. So what this means is that on the 614th position of the protein, because we number the positions, D, which is a code for the amino acid aspartic acid, changed to a G, which is the code for glycine, which is another amino acid. And this just single change was enough to make that conformational change. So we just talked about how, okay, this will affect how strongly the virus binds. But even more worrying aspect of mutations is mutations that might affect the ability of antibodies to bind. So antibodies are those things that your body produces in response to infection or vaccination. So if you get a vaccine, your body produces antibodies. It helps combat the virus by blocking it or tagging it for elimination for the rest of the immune system. If your vaccine contained one form of the spike protein and the virus mutated to another form, the worry is that this binding wouldn't happen as strongly and as originally thought. So there have been a couple mutations that have happened. That the first one that was identified that had concern over this antibody binding was this N501Y, which is more commonly just called the UK variant. It had a mutation up here at the top of the protein, which was worrying about, the antibody, blocking that antibody response there. So the other mutation, it's E484K, and it's seen in both what we call the South African variant and the Brazilian variant. And, we're still trying to understand more about them. It seems that there are other parts of the protein that are still binding just fine, but it's been shown that the virus is doing it, and maybe the next mutation might be even worse. So we just don't want this to continue happening. What hasn't been identified yet, but is theoretically possible, is you could get whole deletions of the protein. So here's a picture of a N-terminal domain deletion that could potentially happen, where the virus doesn't necessarily need this part of the protein to enter the cell. So it's possible that a mutation could delete this whole section. And in that case, what used to bind here wouldn't even be there to begin with. So that's kind of the goal at the moment of the public health measures, that you just need to eliminate the pool of virus that's replicating out in the community, so that we kind of stop a lot of these mutations. Like, a lot of people think like, well, I don't mind if I get infected. I'm healthy. I'll be fine, and that's true. You might be fine, but your body is still producing virus, and it's still producing potentially mutated virus, and that could be a big problem in the community and even the world, because any human that's getting infected and making virus has the potential to produce one of these. And it's not something that we want to happen. So that's why leaders around the world are starting to become concerned about vaccine supplies reaching underserved regions, because hypothetically, one may live in a country where everyone is 100% vaccinated. There's no problems. The virus isn't circulating in that country. But if it's still a big problem in another country, the virus could still be mutating, and then all of a sudden, it gets past everyone's vaccination in the next door country, and that's no good for anybody. So the kind of press to get vaccines to the entire world, not just some parts of the world, is kind of the thinking of trying to eliminate some of these variants. So let's see here. So I'm going to just talk about those two topics, and then conclude with one more thing about vaccine hesitancy, as the term now is. So being nervous about vaccines is becoming more common, and more commonly talked about, at least, especially in the post Andrew Wakefield world, where it was first kind of, for those of you unfamiliar, Andrew Wakefield is the doctor who incorrectly tried to make a link between vaccines and autism, and his papers have since been discredited, but like, that idea was still persistent in people's minds for, still today. But vaccine hesitancy it's not necessarily a new thing, based on some data gathered by polls in the United States. What's interesting to me is even in 1954, with the polio being a huge fear, people were still a little bit hesitant about, taking these new vaccines, compared to, you'd think everyone would be very excited to finally be rid of these fears of polio. And I was surprised to see, too, that I'm like, oh, why was this poll taken about smallpox in 2002? And then I remembered, oh, yes, in the wake of the bioterrorism scares of 2002, there was talk of revaccinating the country for smallpox, even though smallpox had been eradicated. And people in the United States, I believe, hadn't been getting smallpox vaccines since it might have been the 70s. So smallpox was basically eradicated in the United States before that, but smallpox vaccines were still given out because it was still prevalent in the world. But yeah, most people born after a certain year, have never had a smallpox vaccine. So even though it was a proven technology that, millions and possibly billions at the time that people had gotten, there was still a lot of hesitancy about it, and continuing into the swine flu. So, even today you see your celebrities and world leaders kind of show, publicly posting the pictures of themselves getting the vaccine, just like Elvis here was doing in the 1950s. So let's see. So it's a big ask to have healthy people get injected with a substance that they don't completely understand. So it seems that if we look at some poll data taken in September, this was September of 2020. Lack of information seemed to be the major roadblock for people's confidence. It's taking time for everyone to get up to speed on all this new information. And I can understand why, doing something that is new could be scary, because it seems like, we as humans, it takes us a little bit to warm up to new things. I got some data from a second poll that was a little bit more recent, that was published through CBS News, that seems that, like, just between September and now, it seems that people are getting a little bit more confident, but we're still seeing some hesitancy in these, kind of uncertainty about understanding what exactly is going on with vaccines and is it okay. But I have confidence that, like, when the supply demand problem is done, that confidence should be up. And when people start talking to their family and friends about it, that they'll feel better, especially when it comes to some of the trust issues that are seen kind of down in the bottom of the graph here. I can certainly understand, especially in communities that have been harmed in the past, specifically trust issues in the Black community in the United States, with the Tuskegee syphilis experiments. Those really eroded trust, and it's just stressing the idea that even if you don't trust, the government or trust vaccine manufacturers, like, surely as more people in the community go through the process, the message will get across a little bit better than from, like, the governor or a drug maker. So once again, I didn't want to, kind of have too much information in the formal presentation right now, because I figured, we'll probably just want some time for discussion. So I guess I can, I'm just going to change my screen so I can see everybody better, and then maybe we can have some questions here. Oops, hold on. I'm going to stop the share. There we go. Yes, would anyone like to hear about something that we didn't talk about, or elaborate on something that we did discuss?
Yes, I have a question about what causes mutations. Is, you said it's in obviously without mutations there'd be no evolution, and we wouldn't be here the way we are now. So. But it's caused by copying errors, you said. So is there any way to increase or decrease the likelihood of copying errors, or is that just completely random?
Well, it's completely random. And the reason that it happens in our bodies with DNA all the time. But DNA has a lot of safeguards to prevent copying errors. A lot of people that are predisposed to cancer of various types, genetically predisposed, is because they lack some of these safeguards to prevent the copying errors. So while you're born cancer-free, it's sometimes only a matter of time before you get a copying error because you just don't have the same protection as another person who has the gene for the protective protein. When it comes to making RNA from a piece of DNA, there's usually no safeguards to prevent copying errors because it's usually not a big deal. You make a piece of RNA and then the protein gets made. And if it's a bad protein, it's not the end of the world, because you'll make another one and it's okay. But with RNA viruses, that's a problem because they don't even have DNA. They just have the RNA, which is very prone to, when it's being copied to make new viruses, it just gets full of these errors. It's a random process, and like the vast majority of them don't make it, but ideally we'd like to turn off the ability for the cells to make viral RNA. That would be great. But if the cell's going to be making the RNA, then the copying errors are likely to happen. We see this with flu. That's why we need these yearly vaccines, because flu's different. It has a lot of different strands of RNA, but it just develops so many changes that it's hard to keep up with it.
There's a question in the chat.
Oh yes, I see it down here.
Okay.
All right. Okay, so this is a question about CRISPR. So CRISPR is a new technology that is kind of making it possible to insert new genes or take out bad genes and put a good one in. To my knowledge, I don't think that is being used in vaccine development at the moment. I think with the current vaccine development for these new RNA vaccines is just, you don't even need a piece of the physical RNA from the virus. You don't have to isolate it. It's just, you could just have a digital file and send it to a lab somewhere, a digital file of the genome. And then you can have a machine make the RNA, and then you can pack it into the little lipid nanoparticles. So the idea is that if you can make whatever piece of RNA you want. Like if you want to make a whole bunch to kind of anticipate a mutation, you technically could. It might not be worth it. Because it might just be hundreds of different possibilities. It's probably better to stick with a few. Future vaccines, especially with I believe Pfizer is talking about it. It's like, oh, well, possibly a third booster might be necessary. That third booster might have a bunch of different pieces of RNA put in there, as opposed to just one that is now. It's just they wanted to make sure that the version with one worked, and then it's very easy to just have the machine crank out different versions of the RNA piece that you can put in there. Better to do it against something that is an active virus. Variant out there than a predicted one, but it seems to be a possibility.
What type of cells, or maybe it's any cell, actually will receive the mRNA and make more proteins? Is there like a specific cell in the human body that does that, or
that's a good question? So any kind of cell can take it. So in the vaccine, so I might not be correct here because I don't know the exact specifics of what each of the, like, I guess Moderna and Pfizer both have the mRNA vaccines. I don't know if they put any particular tag on the particles to send it to a different cell type or what. I think, as far as I'm concerned, I think it's just general. Like the idea would be like you get an arm injection, and it in theory can go into any cell in that area, and it'll attract the immune cells to there. And then, the immune cells will remember for next time, because like if you were to get a vaccine and then encounter a virus in the real world, you'd encounter it through your lungs, So you're like, well, if the immune response is happening in my muscles, in my arm, is that okay? It's like, that's okay, because the cells travel there, they remember what happened, they produces antibodies that go all throughout your body, and then it doesn't matter where the virus is going to enter next time. Immune cells are very good at getting to where they need to be. They flow through the circulatory system, and they can exit your vein, like through the cell wall, and crawl into the area that it needs to be. Immune systems are complicated and fascinating, and like they're so different in everybody's body, but it is possible. The reason I kind of caveat, like, I could be wrong, is because like there might be some proprietary like helpers that get it to where it needs to go. But I can say that the drug that I worked on was specifically a liver drug, and the whole idea was that it was supposed to go just to the liver and not anywhere else for the RNA to get inside the cell. So, that is totally possible. Unless we got two questions.
Oh, sorry.
It's okay.
I heard that one of the variants, and I don't remember which one, that the one that they were concerned that it's not going to be easily responsive to the vaccine because it causes the spike protein to actually get more tangled.
Oh, so, that's interesting. Yeah.
Yeah. So some of the antigens, or I guess those are antigens. I don't know. The parts that the vaccine would look for, or the antibodies would look for, are hidden inside the spike. More.
Yes. So, that's absolutely true.
Yeah. So I don't know. I mean, is there going to be an approach for some of the vaccines to try to come up with a way would they have to untangle that first? I mean, what are they going to do to try to do they have an approach in mind to tackle something like that?
Yeah. So what you mentioned is, like, I find that very interesting, because I used to work on, so it's like protein folding. Proteins, when they're made, they're like this single string, and then they kind of fold up and they make a unique shape, and certain parts are exposed and certain parts aren't exposed. I used to work with trying to look at protein-protein interactions, like how an antibody binds. And there'd be certain times that in my artificial system that I was studying, like, it's not that the binding wasn't happening. It's just that, like, there was a different pH in the fluid I was using, and the site kind of like buried itself inside of the protein and got hidden. So that happens a lot. The good thing though is that when you do get a vaccine, or you're infected with the virus naturally, it's not just one antibody that gets made. It's a lot for like different parts, So one might bind over here and one might bind like up top. As long as something's binding, it's not like you're completely 100% like susceptible again, but it can be a drawback, because like, then you're still opening up that possibility of like, oh, well, the virus is just getting better at evading things. So, I'm glad you brought that up as an example, because, it's true, you're hiding these areas that might not have been mutated, but still are preventing antibody binding,
You said that there's a machine.
Mm-hmm.
Can you give us an idea how that machine works, what the raw materials are?
Oh, sure. So a genetic material DNA, RNA. It's made of components, 4 components to be specific. I'm sure you've seen pictures where there's like A's and T's and C's and G's, and they're binding to each other. So these like 4 components, they're easy to synthesize in a lab. You can make big pools of them and have them in solution, and you have a sequence, and you can make what's called a primer, which it's a little piece of DNA or RNA or whatever it happens to be. And you can, let me back up a little bit. So there was this amazing discovery called, that they found in undersea thermal vents. And it was in these deep environments where you have like super hot, like exhaust, it was a geothermal exhaust coming out of these undersea vents, and then super cold water on the outside. These organisms survived at the bottom of the sea because they had a protein that was different than the protein that makes our DNA and RNA. It could withstand these wild temperature swings. So normally, our cells are making DNA and RNA all the time with an enzyme called DNA polymerase. And then there's an equivalent one called RNA polymerase that takes all these individual pieces and links them together. And then the problem it's like, how do you do this in a lab? So if you have the RNA polymerase and you're linking the pieces, how do you make another one, after you just made one? Because you need millions and billions of these things that are getting made. So the Taq polymerase is what the undersea vent is called. Because it can withstand these temperatures, you can heat up the piece that you just made and it'll peel apart. And then you can build another one on top of it and on top of it and on top of it. And by changing this temperature to hot to cold, hot to cold, hot to cold, you can get your pieces of RNA to unpeel after you just made them. And after they unpeel, it's very similar to how when your cell makes another cell, everything kind of unpeels and duplicates. If it couldn't withstand these temperatures, every time you'd heat it up, it would degrade this RNA polymerase that you put in there. It would, how I said proteins are a string of amino acids that kind of fold up. Well, when you heat it up, it would unfold because of the hot temperatures. And then when it would try to refold, it would kind of squish itself and it would basically die. So because of like deep sea exploration, this is how like all science is connected. We figured out how to make RNA in a machine, because we have these enzymes that can do the work for us and can withstand this hot, cold situation. So they also discovered, this is totally off topic, but it was it's green fluorescent protein is used in a lot of scientific research in biology and even imaging in the medical field. It was discovered in a jellyfish. So we still use green fluorescent protein today.
So what are the raw materials?
So it's adenine is a chemical, thymine, guanidine, cytosine. They can be synthesized using chemistry. They can be synthesized in space. Some asteroids, those components have been found on them because the energy of the sun can cause certain chemical reactions to take place. Sometimes you're looking for these chemicals for signs of life, but they can form spontaneously on their own. But in our bodies make them with enzymes. But there's certain things that you can't make with chemistry. They're just too complicated in the body. But there's other things that you can synthesize. I made nylon once. That was fun. Just putting the different components together and making that long string of nylon. But then sheep's wool, that's a protein that's too complicated to synthesize on its own. So you can make a fiber of nylon in a lab using no biological components, but to do that with wool, it's haven't figured that one out yet.
Thank you.
All right, let's see. Oh yeah, see, we got a question here, Gary.
There's more than one vaccine out there, and I guess I've heard they attack or attach in different ways. Can you explain a little bit about what is the attack strategy, or where it hooks on, or how they work differently?
All right. So what I didn't talk about at all was the AstraZeneca and J&J vaccines, because I think when I was thinking about this presentation, they weren't even approved yet. And I'm just I won't talk about that. I'm like, whoops, it's a little bit more relevant now. So those vaccines, both J&J and AstraZeneca, use a different technology where it's called a viral vector. So a different virus, adenovirus, I think is what they're both using. Once again, a lot of these, for proprietary information, I'm not sure exactly how it works, but adenovirus is a popular virus to use. It was originally part of a common cold virus that it's really easy to work with. So scientists are like, oh, let's take that virus. We'll take the inside of it out. We'll take all the genetic material out, and we'll load in the genetic material of the virus we want to vaccinate against. So that way, the virus outside will just carry the genetic information of the virus we want to vaccinate into the cells. They'll make viral proteins, and then the immune system will come and they'll see what's going on. When these were first getting developed, it was thought of as a way to do genetic engineering, especially for people with genetic diseases that they're just born with cystic fibrosis, for example, where they thought, oh, let's see if we can take a virus, put the gene, the good version of the gene that a bad version would call cystic fibrosis, and get it into the body. And the problem that they had to overcome was the immune system was reacting to the carrier virus, and not the genetic material on the inside before it could get there. So it took a couple more years to kind of engineer the carrier virus, just so they could get into the body and not cause an immune response too early, because you still kind of want the immune system to come and gather at the spot. But if it happens too early, it'll eliminate it before anything can happen. So with the J&J and AstraZeneca, they I guess the outside is a little different. It's binding in a different way, and I think I'm trying to remember this correctly. Or maybe it's one of the. I think it's the Russian, the vaccine, the Sputnik. They have you'll get a first dose, and then your second dose is a different carrier. So it's in. So if you, for whatever reason, were getting an immune response with the one and it was getting eliminated from your body, the second one would be different. So it's kind of tricked the immune system a little to get in there. But I don't know. I'm pretty sure that the AstraZeneca that involves 2 doses, I think it's 2 of the same. And Johnson & Johnson so far is just the one, which is good, because that's cutting the amount of doses in half there. All right, what do we got?
So the Pfizer and Moderna are basically the same technology, right? mRNA.
Yeah, they're pretty similar.
Do we understand why the Pfizer has to be kept so much colder than the Moderna?
That's a good point. So, okay, I'll tell you what I do right now at work is I work on stability, drug stability, which is kind of where expiration dates come from and where these temperature recommendations come from. So the drugs that I work on, if you happen to ever, see them in their package and they have a certain storage temperature, it's me that determines that. So the problem with these lipid nanoparticles is that they need to be kept really cold, because they kind of move around a little too much. And if they get heated up, they'll melt. So it's almost thinking of like if you have like little like butter, for example. They're very similar to butter. Butter can be solid when it's really cold, but when it heats up too much, it will start to melt and everything will fall out of it. So when I do stability testing, it can take sometimes 5 years to really know for sure how long something's going to last, how long something will still be effective in the body. Because there's a safety aspect to it, and then there's the like, will it work? So safety is always the number one priority. You don't want something breaking down into a harmful form. But then also, even if something is harmless when it breaks down, you want your drug to actually work. So minus 70 degrees Celsius is kind of the standard for getting, like, any drug you store is going to be safe at that temperature. That's always like the recommended temperature. With the Mrna, I don't know exactly where they came up with 20 degrees Celsius is okay, which 20 degrees Celsius is normal freezer temperature. So minus 70 is very cold. That's like dry ice temperature. And minus 20 C is freezer temperature. 2 to 8 C is refrigerator, and then there's room temperature. They either did different stability testing that they were able to say, hey, 20 degrees is safe, or they might have had a different formula that, because there's certain things that you can add to the lipid nanoparticle. Like, so in our cells, the outside of our cells are pretty similar to lipid nanoparticles. We have cholesterol and all kinds of things in there as well that kind of make it a little bit more solid, it can kind of hold the molecules together better. They might have had some kind of ingredient that they made it a little bit more stable, or it could turn out like in 2 years from now or less that Pfizer might say, actually 20 degrees is okay. They just didn't know for sure until they did the testing. Because like Mrna, I don't know how long they had been working on their technology. It might have been longer. They just might have had more data to make that determination that 20 degrees is okay. Because a lot of companies they're just very conservative. It's like they something might be fine, but they don't want to risk it. It's like they'll just say, hey, minus 70, we don't want to risk it. We're just going to play it safe,
That's what I've heard with because I listened to a virology podcast, and they are saying that Pfizer's in the process of getting that reevaluated so that
awesome.
they don't.
Did you listen to This Week in Virology?
Yes, I love that.
The guy that when I was getting my PhD, both those guys actually wrote the textbook that I use.
Awesome.
So I know them pretty well. Jane
Very
Flynn
cool.
was their friend that was my professor. So
awesome. Yeah, it's a great podcast.
Yeah, it's great. Yes, Martin.
So I have a question about the different vaccines are said to have a different effectiveness rate. I think the Johnson & Johnson was once quoted as being only 66% effective. Is that the probability that the end result will, I guess the sub-question is the intended end result, the antibody, identical to regardless of which vaccine? And is the probability of effectiveness the chances that that antibody will be produced, or is it the effectiveness of the resulting antibody?
So these numbers are thrown around a lot, and sometimes, it's not certain, what the context of what that means is. So I appreciate your question because it's like, wait, 70, 80, 95, what's all this talking about? What they're referring to is clinical trials. And in the clinical trials, let's say hypothetically you had 100 people, and by the end of the clinical trial, what's the outcome of those 100 people? So they're not looking at like molecularly what's going on, because when an individual produces antibodies, it is wildly different between different people in terms of like, are they mostly producing antibodies that bind to one site, another site? It's always a giant mix. And the vaccines are made differently, in terms of what piece of that spike protein they're going to use and which sequence of that spike protein they're going to use. So the mix of antibodies is going to be a little different between the vaccines, how strong the immune system is, or how strong the immune response is going to be for each of those vaccines. So, but for those numbers that they usually just throw out there, they're not looking like molecularly what's happening. But in order to understand a little bit better too, it helps that you understand too the context in which the numbers came from. Like, I know the big thing that people got concerned about the J&J vaccine. It's like, oh wow, it seems like it's low in effectiveness, and it's like, well, that one was tested in South Africa during the variant, and it still is 100% effective at preventing people from dying, which is like kind of the big thing we're concerned about. So at this point, it's like, well, when you hear these numbers, make sure you fully understand what that means in terms of, sometimes the goal is just to not get sick and not end up in the hospital, rather than, worrying about like, specifically. But you're right. I am kind of curious, like, once there's more time to really look at the molecular nature of the different vaccines and to see like, why was it that this one, the numbers ended up a little different, just to answer those questions. Because at the moment, we're just really just concerned with the outcome, is this person okay? So, but hey, eventually I'd like to know. All right, what do we got here? We got John with a question.
So what do the percentage effectiveness numbers actually mean? If you had 100 people who have the vaccine, and then you say it's like 80% effective, what does that mean? That
so
80% don't get any symptoms, 80% don't show any virus in their body?
It's tested positive, basically, virus in their body. Okay. So all of the vaccines that I'm aware of, the ones that are approved in the United States, I can't say anything about like the Indian and Chinese and Russian, all the other ones. They are 100% effective against preventing death. So no one in at least the trials that I'm aware of, because these things are always ongoing, that in the period that they tested, nobody died of coronavirus. Then the next thing that you kind of look at is like, okay, well, how many people are hospitalized? And that number was like basically nothing. I mean, I think there was like a couple, but like, but when you look at like just the straight up effectiveness number, some people were testing positive, even though they were vaccinated, but those people tended to have either minor illness, asymptomatic illness. It's still important to know this, because if I'm vaccinated and I have asymptomatic illness, I can still spread it to unvaccinated people. So like a lot of people are upset about like, oh, I'm vaccinated, but I still have to like wear a mask and things like that. But like you don't want to risk, spreading it even more, even though like you might be okay. So, it's just this matter of, until we know more about like, okay, what is a vaccinated person's chances of causing harm to others, that's kind of where we're at right now. But just to go back to that effectiveness number you were talking about, and understanding, where it comes from too. Do be aware too that these things were tested at different times and in different places. So comparing them to each other is sometimes not as straightforward as it seems. So what would be a big deal is if you saw that, like let's say you saw the Pfizer number, and they say like, oh, it's 95% effective. But then, as more people are getting it, more data is getting collected, and then you realize that number is like dropping a lot. That's like, oh, these variants are probably causing it to lose its effectiveness. We might need to tweak it. We might need to add a booster. But if you're comparing the Pfizer to the J&J directly to each other, it's hard to make a similar conclusion, but you definitely want to keep looking at that effectiveness number, so you know when you need to update the vaccine in a similar way that flu vaccines are updated. Because if it drops too low, then you'll have to change it. All right, who do we got here? Maybe got two.
My question is about that. I understand from reading early on that COVID is sort of related to the common cold.
Yes.
And I'm assuming that these vaccines that we have right now would have no effect on the common cold at this point because they're very specific. Is that correct?
Yeah, they're pretty specific, and there are types of coronaviruses that do cause the common cold. The way we classify viruses, sometimes we'll like group them in the categories, but they might be very different from each other in terms of like the effects. So like I mostly studied herpes viruses. That was like my big thing. Herpes viruses are big viruses. They have a lot of different proteins, but they're all very similar proteins. But, one causes chicken pox and the other, causes lesions like on your lips. And, they both cause lesions, but why the one is going in the one area and the other is going to the other, it's just, they're so different. But common cold, like, love to have something to fight that, but there's just so many things that cause the common cold, but hey, with this new technology, like maybe it's possible to start seeing more effective things against these little nuisance viruses that maybe it wasn't worth developing anything for in the past. So I'm excited for what's to come, but we'll see what happens.
Yeah. Well, I was wondering if you could just not, load up these little nano guys with all kinds of stuff to fight the common cold. If we could actually knock that one out as well.
Yeah, that would be great. So, so I didn't talk about this too much earlier, but I want to mention that this was a unique time for these clinical trials in that, so there has been work on AIDS vaccines for years. Like I think ever since, AIDS was HIV, the virus that causes AIDS, was first discovered, work has been done to get a vaccine for it. Now, HIV has a lot of problems with making a vaccine for that. It's a totally different story. But at the same time, like sometimes it's hard to test because there's certain populations and regions of the world where HIV is spreading more prevalently, but it just takes so long to identify the infection, and like it takes years, by the time you can figure out whether your vaccine is actually working or not. So you'll give it to a healthy person and maybe somebody that's high risk, but like they might never contract HIV, just, going through their normal day. So then you're like, well, how do we know that it worked or what's going on? But with COVID-19, it's like, well, it's just all over the place, and if you do nothing to protect yourself, no social distancing or masking, like chances are you're probably going to get exposed, at some point. So like, it wasn't difficult to take a group of people and, just doing, normal life and say like, all right, is this working or not? So, it is possible to make other vaccines with the same technology, and hopefully we can get something, but you might not see it as fast, just because of the nature of getting infected and exposure and things like that. All right, we got Ro has a question.
Is there a place where we could read the official report? Because with the J&J, I don't know whether I'm reading it wrong or it's inaccurate reporting or what's going on, but there were 0 deaths, 0 hospitalizations. But some people got serious disease. what do they consider serious disease if nobody was hospitalized?
That's a good question, because in like, let's say the technical language, and this happens all the time in like nutrition versus like, the technical or the language that we use every day versus like the technical language. It's like, okay, what does minor mean and what does serious mean, and I don't have like that information off the top of my head, but yeah, it's like serious could mean something like missed days of work. It's like a real impact as opposed to like I had a sniffle, or something like that, something that didn't like really like impact your day to day, but still was something that you could record. A lot of times it's like somehow you're prevented from doing an activity that you would normally do, usually like earning an income in some way. That would be like a missed days at work, which can be serious because you might need the money. But so yeah, I'm sorry I can't provide you the specific definitions that they're using. But yeah, it's usually some kind of criteria that falls in a particular category. But the other thing that people get confused about too is considering side effects and adverse side effects and minor side effects. And it's like, well, here, how serious are we talking here? I had a dose of the Pfizer vaccine, my first dose, and I felt lousy, but that's considered, a minor side effect as opposed to like, I knew somebody who like couldn't move their arm because it hurt so bad type thing. That I was considered like a serious side effect, and to hear the word like serious and be like, does that mean like permanent disability serious, or does that mean like, have to go to the hospital serious? So yeah, to like the everyday, conversation, it's hard to, talk about.
Is there a place where they're published?
Oh, yeah, sorry, you didn't ask that. So yeah, I off the top of my head, I wish I could give you more information. I would recommend the CDC website has a lot of the technical language, and they try to make it accessible to everyone. But yeah, specifically for like Pfizer or J&J, like what that entails specifically. But I would consider going directly to their sites.
The FDA.
Mm-hmm.
Okay.
Yeah, because the FDA actually makes these decisions. Got anybody else out there? All right.
Is there absolutely no sharing? I mean, you've mentioned other countries have versions of the vaccine as if you don't know or we don't know what they're doing. Is that the fact? So
a lot of vaccine politics, and I call it vaccine politics, it gets a little funny sometimes. It's about like, governments will make a certain pre-order of vaccines, based on a company that's in development, and it's just a matter of waiting for approval, so that you can actually start using it in your country. So in theory, if the United States government wanted to buy, a vaccine from, Russia or India or something like that, like it's theoretically possible, but then it would have to be approved in this country with our FDA. So the Astrazeneca vaccine, it's a big topic of conversation in European countries because that's the one that the EU specifically made a deal with. And there's all kinds of other stuff involving vaccine exports and whatnot. But ultimately, the European Union equivalent of the FDA has to approve it. So eventually, you might see like AstraZeneca vaccine available in this country too. It's just a matter of whether it gets FDA approval or not. And the same goes with other countries, like Mexico has its own version of the FDA, Canada, and, all throughout the world. So how they determined, so a company, like let's say I'm J&J, I have to submit my application to the FDA for approval, and then they'll start going through the process. Sometimes it's a lot more paperwork or data that you might need in order to submit that packet. So J&J could have been like, well, we're submitting it to another country first, or simultaneously, depending on their business strategy. But yeah, it's kind of this whole separate thing that can get a little get a little dramatic. The drug approval process and different regulations. I know in my line of work too, I might need to, let's say, do a certain test, not because it's required in this country, but because it's required in another country, to try to get it like on par with more, to be able to distribute in as many countries as possible.
But the science is shared.
The science is shared. Well, I mean, there are some companies that have gotten some criticism for not being as transparent as would be helpful. So the World Health Organization put some companies on the naughty list, for their lack of sharing. But others have been a little bit more agreeing to that. Because once again, when you have private companies doing a lot of this, they're not required to share anything, but a lot of collaborations with universities have kind of helped this move along a little bit better. So the example is that the Astrazeneca vaccine in the UK is a collaboration with Oxford University, and Oxford would not agree to any kind of situation where the information wasn't shared, because their mission as a university is to advance knowledge in human health. So, but other companies, that's up to them, and the World Health Organization is getting on them about that.
There's another question in the chat.
Oh yes, I do see a couple more here. All right. Yes. See something. Oh, herd immunity. Is that the question? Okay. So, yeah, herd immunity is that another one of those terms we throw around a lot. So, in an ideal world, whatever the disease might be, let's say like polio, for example, something that's already been basically eradicated. It's like, well, in an ideal world, we'll say like, let's vaccinate everybody, 100% of the people. That way we can be sure that we won't have this virus anymore. Because ultimately, we want to get rid of viruses. We just want to eradicate them if possible. Certain viruses, that's harder, but we want to get rid of them. So, but giving vaccines to 100% of people is not possible most of the time for various reasons of certain health conditions prevent people from mounting an appropriate immune response that a vaccine would work. Some people don't have proper access. Newborn babies a lot of time can't receive vaccines for various reasons. It's like there's always going to be some kind of reason that 100% of the people in a population can't be vaccinated. But you don't necessarily need to achieve 100% vaccination to eliminate a virus because of this thing called herd immunity. So if I'm somebody who has an immunocompromised system and I can't get a vaccine for various reasons, that's fine. But if everybody in my community is vaccinated, I'm okay, because like there's really nobody that can pass the virus along to me. And there tends to be different thresholds for herd immunity depending on how contagious something is or the nature of it. So these numbers can change a little bit depending on the exact virus type, but it's kind of this minimum number that like you don't have to worry about it anymore. The population is basically protected, whether that's already being infected with the virus and being immune, or getting a vaccine. So, like, I've never received a polio vaccine because polio is basically gone in North America. It's still, vaccines are still given out in parts of Africa and India because polio still exists there. But, we were so good from the development of the polio vaccine to, administering in North America, that we now don't even need vaccines. So it's like the idea of like herd immunity can get to a point where the virus is basically gone from the community, and then you don't even need to have protection anymore. But, there's some countries that Sweden is the big example, that their kind of idea is that, in the meantime, while vaccines are being developed, we'll just see, how much, herd immunity can happen by people naturally getting infected. So if you're susceptible to, or if you're at high risk for complications or dying from COVID, then, you can do all the social distancing, but other people just go out and do it. But it doesn't seem to be, working like they thought. So, but that is kind of the idea, that like herd immunity can be achieved through just people being infected and immune, or vaccinations. So, I'm seeing a thing pop up here. Meet somebody at the airport, you'll still get it right. Oh yeah, so with polio, yeah. So it can travel, but usually the people that are getting polio are people that are in very remote areas, and it's one of those to get, like, say for example, if I want to go to India, where polio is in certain communities, not all the country, but just certain communities, I would be required to get a polio vaccine before I would be allowed to travel there, because there'd be a risk of me bringing it back. So countries that require various visas and whatnot to go, usually that is a requirement. So people from parts of the world that have polio endemic in their countries, in order to get a visa to come to the United States, they need to have a vaccine. But it is possible, because we still you can still get a polio vaccine for whatever the reason happens to be. You're traveling or whatever. But if you're just going about your daily life, nothing special, then it's not necessary. In the same way that most people don't get rabies vaccines unless they work in a high-risk area or have already been exposed to rabid animals. But like, it's totally okay to get a rabies vaccine, just in case. But for most people, just not really necessary, So you'll do just fine without it, unless you're a vet or somebody who works with animals in some way. So, yes, I see Paula.
Oh, I was going to say with the herd immunity, they also said on TWIV that because children are 25% of the population, we really are. It's unlikely that we'll hit herd immunity, because with not every single adult getting vaccinated until we start vaccinating the younger population.
You're right. I'm glad you brought that up, because children, like 25%, very, very large percentage. And right now, the youngest that we're going with the vaccines is 16 with the Mrna, and it takes a lot longer to test and do clinical trials with children, but hopefully we'll see that change. They do it in different age groups. They'll do like, I can't remember exactly, but like the older kids, and then they'll start getting younger and younger and younger. Babies, it starts to get kind of hard, but it's fairly normal that babies aren't getting too many vaccines when they're newborn. Anyway, if you can get most of the younger children, then you can get enough protection there. Where if all the adults in a baby's life are protected, then there's really no opportunity to get exposed. So yeah, I see a question popping up here. Or just a comment about people potentially shedding virus after being vaccinated. This is one of these things that we're not sure of yet. How a vaccinated person will how much virus a vaccinated person will or will not be producing. So that's why we're kind of playing it safe with some of these public health measures. And I feel like sometimes, like in news reports, it gets a little like doom and gloomy. It's like, oh my goodness, you'll have to be wearing masks for the next year and a half. It's like, well, let's just play it safe. It's just until we can figure out how it's working exactly. Doesn't really hurt, to just play it safe and get better data before making any major decisions. But hey, what's the whole point of all this that we're doing? It's just preventing people from having long-term impairments. People from dying, people from ending up in the hospital for weeks. If we can just not have to be afraid of those type of things, all the little things can come later. But right now, just kind of focus on the big picture here. You want to stop all that, and then we can kind of work out the little things as we go. Once we get kind of further along. All right, Gary.
It seems like there's not a comprehensive program of registering when you've had vaccinations over time, because I had to one time reconcile records and it was nearly impossible to find stuff. And they even said, well, we just didn't document it because it was presumed that you got chicken pox. And I remember it, but if there was somebody to vouch, it was kind of like in this gray area for medical. Like, do you have to get the vaccine, or can you just say you were born for a certain age? Why is there no comprehensive registry? Or is that it can't get funding, or it's too politically hot mess because of personal privacy issues?
I'm glad you brought this up, because I feel the same way. Because it's like, I feel like medical history in general is just like, so can you tell me a little bit about? I'm like, I don't remember. Like I was a child for like half of this stuff. I had chicken pox, but like it was like 3. One of the big complications with this vaccine rollout too is like keeping track of all these people and making sure that somebody who got one type of vaccine like knows that they have to get their second and gets the right kind, and knowing in the future, like, if a company decides we're going to do a third or whatever, that like they stay consistent. But I think the big deal with the medical records in general is just in the past, it all had to be done on paper with paper records. Now we have the ability to have things digital, but with privacy concerns and just kind of having a unifying force, kind of pushing everything forward, whether it's like a federal government thing or because I think, unfortunately, a lot of like insurance companies kind of develop kind of the way things need to be. But it would be nice if so for example, we have a federal system for Veterans Affairs, VA medical stuff, and even like the Medicare system, that you can have these records, you can keep track. It's just a matter of having a centralized system like through the government that's willing to do it. Other countries have a little bit easier time, like in the UK with the National Health Service, like things are pretty streamlined. Like, for example, if I feel sick, I just call this number and they automatically have all my information, and they're like, oh, just go to this hospital, and they expect you there and they have all your stuff. But now I'm like, well, let's say I'm diagnosed with an allergy of something, like, let's say I'm allergic to like penicillin. It's like I show up at the hospital, it's like, so you allergic? I'm like, you should be able to tell me, But I guess it's just a mess of state government entities and trying to get this moving without doing it too fast to blunder and then have it all vulnerable, to any kind of like security issues, But I do wish it could be easier in terms of records. I don't even know what my permanent record looks like half the time. Oh, we got another question.
It's time for a little humor here. Can we make the analogy that I've seen on Facebook where there's a peeing section in a swimming pool?
Oh yeah, I saw that. Yes, for those of you, I think it was Neil deGrasse Tyson did a post about it's just the different states, all having their separate rules, and it's like when you're looking at like one country, it's like it's almost like saying that there's a peeing section of the swimming pool. It doesn't matter what one state does if their policies are like, let's say, too lax. It's going to affect its neighbors too. And I understand that some people say like, oh, individuals should make their own decisions, but like consistent messaging it's been a problem since the beginning, because it's just like, well, is this okay? I don't know, even like, especially, where I live, like I live like right on the border between like Pennsylvania, New Jersey, and Delaware. And I work in Pennsylvania and I live in New Jersey, and like my family lives in Delaware, and it's like, wait, what am I doing right now? What's legally required versus what is, do I have to it's becoming challenging, but I think it is getting a little bit better, in terms of consistent messaging. But people are concerned about even in New Jersey where I live, like things were going really well with decreasing cases and everything, but it seems to be like plateauing out a little bit. Like we made so much progress, and now it just kind of like is hanging there, despite New Jersey being really great with its, well, I don't say like really great, but like, let's say better with its vaccine rollout, in terms of like, we have like 9 million people in the state. And I think they already like gave like 2 million vaccinations, at least first doses. I'm like, oh, wow, that's a pretty big chunk of like the entire like population, but we're still like having trouble getting that, last couple cases to keep decreasing. So, we just got to keep on going, even though, it looks like progress. You can't let up too much, Yes, Paula.
All right, here's my fun question for you, because I know you have your collection of stuffed animal viruses. What cool and nerdy masks do you have right now?
Nerdy mask. Oh, I mean, I have like a Ninja Turtles one. I love Ninja Turtles. I guess I don't really have any like super nerdy like science ones, even though I see them. I have an octopus one where like it looks like the tentacles are like coming down, and I have seasonal ones, of course. So when I'm feeling a bit tropical, I have like my pineapples with sunglasses on them, But I do like to have fun with this sometimes. But I do get slightly envious of the people that are all like color coordinated with their outfit, and I'm just like, I want that.
I am not color coordinated, so I just have some fun ones.
I like to wear the fun ones. And they're even selling some like let's say more PPE, like medical grade quality ones with fun designs, because there's no reason it has to be like white. There's no requirement. It still works just as well when it's a little bit more personal. But if you wanted to do, if you're the person who wants to try double masking, you can have your one underneath and then the fun one on top, so go for it. But so the Ninja Turtles one is significant to me, because when I was like, I was probably like 5 years old. I loved Ninja Turtles so much, but like that wasn't for girls. That was a boys thing. And I was like, no, Ninja Turtles is for everyone, you know?
I like the Ninja Turtles too.
Yeah. It's like anybody can like Ninja Turtles, you know? Just go for it.
There's a question in the chat.
Oh yes, I keep forgetting to look over at the chat. Let me I think I have to scroll. No. Oh, where do you get the best masks? So I think it was like back May of like last year. It took so long to get something fun, you know, like I would like order it and, you know, wouldn't get it for months, but I think it's getting easier now. But yeah, like I feel like so many companies and individuals, you know, are getting, you know, like fun patterns and materials. But in terms of like just effective at like, you know, preventing droplets and aerosolized particles and things like that. So just, you know, to be serious, like the most effective thing that you can wear is an N95 respirator. However, there are disadvantages to this. You know, for much of this pandemic, those have been kind of reserved for healthcare workers and people that are exposed to the virus most often. You know, they're like right in the thick of it. With vaccination, that might be like not as the vaccine, the supply might be letting up a little, but if anyone's ever worn one of these before, like they are actually quite difficult to function in. Like it is, if they're fitted properly, like, and you're wearing them for hours, you know, it can get a little lightheaded sometimes. Like when I used to have to wear them for work and like it wasn't recommended if you had like a heart condition or something that would put extra stress on your body. Like they work great against just about anything, but you know, they're not the most functional things. And it's kind of like, you know, there's a similar saying that's used with a lot of like safety PPE or whatnot. Like, oh, the best helmet is the one you actually wear. You know, the best mask is the one that you can actually wear properly. You know, wear at all times. Is like the comfortable for you to the point where it's not going to fall down or you're not going to be like adjusting it constantly. So like, I guess like the next tier down, you know, in terms of masks are, there's the KN95, and I think I have one over here, but I don't want to like, you know, get up. They're not as thick as the regular N95 masks. There are countries, yeah, there you go. There are countries that they are required, you know, that you wear them out in public spaces, like either a surgical mask or KN95. That's not the case in this country, but my husband was recently in Germany, where that was the rule. You know, anywhere in public building, public space that had to be worn. You know, you couldn't wear the cloth masks anymore. You know, then you kind of get down into like the surgical mask category, but surgical masks still need to be, you know, fitted as well as they can. Everybody's face is a little different. And, you know, a lot of them are supposed to be one size fits all. Like I've seen a lot of like internet hacks of like, oh, you know, if you tie the thing or you do the thing, you know, like, if doing some of those, you know, works for you to get like a good fit, then that is, you know, a good thing to try. You know, however your nose piece is adjusted, because like I said, we're all kind of just different shapes and sizes. And, you know, I wear them. I wear surgical masks. They seem to work best for me. I can wear them all day, you know, when I'm at work. Usually in certain situations, I might choose to wear something else. Like I was taking a walk outside the other day and I have this I have it next to me now. It's a wool one that kind of comes up above my whole face that was designed to be like a public health style mask, but like actually kind of doubles as like winter clothing as well. So I did like it. Yeah, like if at the bare minimum though, you know, like cloth masks are, you know, better than nothing. They do work in a lot of places that they are legally required. But if you want to go better, you can do some of these. Let's say what's the technical term is like non-woven fiber is the technical term for like the kind of medical manufactured kind. A good strategy is you'll have that, and then you'll maybe have the cloth one kind of on top of it, just holding everything together. Whatever works best for you. Because like, once again, the best solution is just whatever you will wear. Whatever will be worn correctly, and especially like kids too. They have different preferences to what they're comfortable with and what they prefer, or whatever the situation might be. See, we have another thing down here on the chat. Just some comments. I know that the eye thing is a big one for me if I'm wearing glasses or safety glasses. With fogging, I've come up with a couple solutions, like laying. It's kind of like a tissue. It's a thing we use in lab called chem wipes. I lay it on the top of my nose. But these things can be tricky to find the right stuff. Let's see. The 3D printed thing that holds the ear loops. My husband uses an ear loop thing because the surgical mask that we bought a big pack to share, and my face, I feel totally fine. I wear it no problem. I don't really need any modifications. It digs into his ears in a way that like his face is just bigger, his head is just bigger than mine. And I'm like, I don't understand what the problem is. But then he bought this thing to kind of connect it so that he doesn't have the discomfort anymore. And he's like, he got a whole pack of them. So there's all kinds of, there's like these kind of, I think they might be 3D printed as well. They're like kind of like this little basket that kind of supports the mask under your face. In the beginning period, like let's say last spring, I did all kinds of like trial and error to see what was working best for me. A lot of people if they're just going to the store or whatever, it's like 45 minutes. But like if you're the type of person who has to work like all day with it, depending on the environment that you're living in, it's best to be comfortable.
While we're on the subject of masks and materials, one of the reasons why I don't have any of these fun design masks is because everyone that I've looked at has been polyester. And I have big questions. They say that 100% cotton is the best for absorbing the droplets, et cetera. So is it counterproductive to wear something that's got a lot of polyester in it?
So cotton does work well. Cotton is pretty great at absorbing to the point where like all these like athletic clothing, you don't want to be wearing cotton because of how great it is to like absorb and hold that moisture. So with the polyester, you're right in that for the same reason you want to wear polyester for athletic clothing, it might not be as great for masks, but it's still something, and I think the main thing is for inevitably you're going to touch the mask, you're going to pull it up a bit, you're going to adjust it, because it's better to adjust it than have it like hang down, and it's the touching can be an issue. With the polyester, how you're kind of getting a lot of it, you're on your hands and whatnot. But and also like in terms of the droplet hitting the polyester and maybe kind of bouncing back and going up, through a crack or something in it. But it's still doing something. If you like your fun pattern, but they happen to be the polyester, and if you're willing to do a double mask, they're still possible, Oh, you're muted there. Oh, there you go.
I sing in the Bach choir, and the Bach choir wants to do something again for some event in May, and it would require starting at the end of March to do something. I get my second shot by the end of March, but I would still possibly be able to infect someone unless we hear otherwise by the end of March. Is that correct?
Yeah, I mean, until there's more information otherwise, it's recommended you still take the normal precautions. But hey, if you're around people that are also vaccinated, you'll know that you have a much lower chance of like hurting somebody else. But it's just going to take a little while to have the point where there's a significant pool of vaccinated people. But it's I'd say that the risk is probably lower than if you were not vaccinated. So it seems that a lot of people that are depending on even if they have like an asymptomatic infection and were infected by the virus without a vaccine, they still have this pretty big viral load that they're shedding because they had no like previous immunity, no antibodies. But with a vaccine, like you could still technically be shedding virus, but not like a huge amount of virus as if you had nothing before. So it might be the difference between like somebody living in your home getting infected from you versus like that person's around you all the time, in the same house, versus if you were to go practice with the Bach choir, like it might be you're around people for a shorter amount of time, and it might not be as significant. But I would still follow any kind of precautions until more is known. All right, we got Gary down there.
I'm kind of curious about the group or social psychology of the progression of a disease like this, and what are the outcomes like? I guess one I could look at is like you see Sesame Street came out with characters that were COVID compliant. I see billboards being changed that are COVID compliant, that now that's kind of the new norm, that somebody had to shoot all that new material. And then looking at something like Ebola and more recently, Ebola that went that through. What is the progression of a group psychology and how do they change, and who's the first one that's going to kind of cross a weird barrier? Because I know after 9/11, it was really hard where the first comedian made a joke that related to 9/11. Like, what is the process of breaking those barriers or becomes part of the group psychology of the past?
Yeah, that's an excellent topic, because I think about a lot like kind of collective trauma, and how it affects people differently. And, when someone's ready to move on with that, and you were mentioning like with comedy and whatnot, it's like, so when it comes to comedy, it's always about like, maybe a little bit of self-deprecation, maybe a little bit of, punching up to authority, but then you never really want to be like punching down to somebody who is really having a hard time. So yeah, like when these things, start to become like, socially normal. But I do think that there will be kind of like this slight lingering anxiety, with a lot of things. People have in general been becoming like very more like germ conscious, and especially people that maybe were a little germophobic to begin with, might be having some issues. But it always does. Help me to, kind of conceptual, kind of process emotions by like kind of learning to laugh about it. But yeah, this is it's all something that's not like the idea is not new, but this specific situation, is hard to say how it's going to go exactly. And even to the point too where what is it like? I feel like when you have conversations with somebody and they want to, just describe a story or something, there's like this fear of like, oh, well, I don't want to be seen as like the non-compliant person. So I'll be like, oh yeah, when I was out at the bar with my friends, but this was at the before time, like really stressing that, or like, so I was in the park the other day and I was following all the rules, I swear. I'm like, I feel like you don't need to like, don't worry too much, but some people do like have this, kind of anxiety about like, I want to be able to talk about my life, but I also have to list the steps, but don't worry, I was being responsible, so I don't know if there's anything else you wanted to touch on there, or anything I kind of, missed with that.
I guess is there a field that actually studies this as a full-time job, for lack of a better term?
I'm sure there are people that specialize in it, in particular, like it's more like a sociology kind of study. But there's a people out there that can get really specific, and like they'll study like how infectious disease impacts financial markets or something, that it's pretty specific, but yeah, it's out there doing it. But I can't give you any, specific people or examples, but yeah, there's certainly experts out there. Oh, we got somebody on mute here. Oh yeah, Ro has a question there. I think you're on mute.
Okay. There is a lot of research that's being done on it. And one of the books that was published supposedly for the general public, but it's pretty technical, is called Denying to the Grave. And it's a little different from what you were talking about, but it's how to reach people who are anti-vaxxers, how to reach people who know that it's not cancer until the doctor says it is, so they're not going to go get tested if they suspect. People that do, smokers and alcoholics, and how do you reach people to get them to modify behaviors? How do you get them to believe the science? How do you reach them? What are the best public health messages? There's a lot of research being done on it. I haven't followed any of it except what was in the book. Again, it's called Denying to the Grave.
I'm glad you brought that up, because that's an excellent topic. And, it's, I think about this all the time, in terms of, I want to give the best message possible. But sometimes it's very hard. It's like this behavior I see a lot, in that it's like people so badly just don't want something to be true, that it's all their excuses are just kind of like grabbing desperately, no matter how, silly the excuse sounds. But, the biggest kind of takeaway I got from people that try really hard, people that are better at me than kind of coming up with strategies for these messages, is that like shaming people is not the answer. That usually ends up making people like kind of back away even more. I guess it was, I listened to the Freakonomics podcast, and they did an episode on this, and I think it was related to a lot of different topics or types of denial that people get in. And what usually helps from like the outcome of their investigation was that kind of letting the person talk, that you're like maybe trying to help, whether it's something with their health or other behavior, and like just really asking them questions like, oh, okay, so explain to me why, trying to get them to explain why. And sometimes when they hear, the more they hear themselves talk and they realize they can't explain it, like they'll start to come to their senses a little bit. I'm trying to think of a specific example, but it's like, it's the idea of, if you ask most people, like, how does a pencil work? most people will be like, yeah, I know how a pencil works. Everybody uses a pencil. But then like when you really start asking like really specific questions, it's like most people can't really tell you like, oh, well, like the molecule of graphite on the top peels off. And then, so like you start to question like, oh, do I really exactly know how this works? So it's kind of allowing people to, when you start to really question them, but then have them talk. That seems to be a better way than to be like, well, you got to do this and you got to do that. And like, most people don't like being told what to do, but, kind of forcing someone to come to their own conclusions is usually a little bit more effective, but it's hard. Like I admit it is very hard. It's, if it was easy, I think we'd overcome it by now. But yeah, there's some things in life that we just don't want to be true so bad, but it kind of doesn't change the outcome. Yeah, I'd be happy if anybody else had any other thoughts on that, because it's just such a hard thing to deal with.
Well, we're after one, going over a little bit.
Really? Yeah, that's why I was like, I'm gonna try to keep the formal presentation short. I know we'll probably have some.
I'm glad you did, because we had plenty to talk about. So, I would like to thank you for giving us this talk. It was really very well done, well appreciated. Hopefully, we won't need a follow up a year from now.
Oh yeah, maybe we can talk about something else.
Yeah, it's great. So thank you everyone for attending, and see you at one of our next events.
Thank you, Danny.